Okay, so in this short video, I'm going to present a particular result that we have obtained in the context of the Max Planck research group on stochastic partial differential equations, which I am representing in this context. Before diving into the actual topic of this talk, I should give credit to the full group. So, of course, there are several members of this group, and so here you see the pictures. So we have 3 postdocs at the moment and 1 PhD student. There have been several former members in this group, and I refer to the SAB report for all of the details and their subsequent positions. So besides of the current and former members, there have been several corporations which have been grown out of this Max Planck research group, which connect also different groups at the institute. Again, here I'm just pointing out the pictures and refer to the report for all of the details. Okay, so now let's start having a look at the content of this talk. So here I'm going to talk about a result connecting fluctuations in non-equilibrium statistical mechanics to the field of stochastic partial differential equations, which then will eventually lead actually to questions in the field of deterministic nonlinear PDEs with irregular coefficients. And I hope that because it connects nicely these kind of different fields of applied mathematics, this can find the interest of several of you. So the starting point is a classical one in statistical mechanics. We start from an interacting particle system. So this is on the atomistic picture. We think of having atoms that interact, which are here idealized in terms of these dots displayed here on a discrete lattice of size n. So the picture to have in mind is that we have atoms. They do decide to go left or to right in a stochastic way. So this is a random system of interacting particles. And typical examples of these would be so-called exclusion processes and also the zero range process, which we will focus on in particular in this talk. Now, the initial question is how to be able to say, make statements about these interacting particle systems when there are a lot of particles, because then the actual simulation of the particle system itself is too costly, because we would have to simulate billions of particles and their interactions. So the idea is that one changes the viewpoint from an atomistic picture to a macroscopic picture by looking at these atomistic interactions from far away. So this would correspond to taking a rescaling of the system, passing from the discrete level we see here on the left-hand side to the macroscopic picture, so to a spatially continuous picture on the right-hand side. And the idea is that although we lose some degrees of freedoms from the actual exact atomistic interactions in the macroscopic picture, we still capture some of the effective dynamics. And this can be understood precisely mathematically in terms of looking at the so-called empirical density field. This is nothing but saying that we look at the empirical density of this discrete picture here and saying that this converges in the limit to a deterministic function then of continuous space. So here on the left-hand side we have something discrete, and here we have something continuous in the space variable. And in addition, on the left-hand side, we have the density of the particle process. So this is a random object, whereas this on the right-hand side is a deterministic object. So the statement we see here is a statement of concentration of measure onto, if you want, a Dirac measure where probability or stochastic effects have completely vanished. And this limiting object can be described exactly as the solution to a nonlinear diffusion equation, so to a nonlinear partial differential equation. So in seeing this, I think there are 2 questions that appear from this. First of all, the question, well, if we accept that this limit function rho bar is an approximation to the actual physical system mu n, then the question becomes how good is that approximation? Meaning that we want to quantify how big the error is in this convergence. The second aspect to draw attention upon is that we start from something which is stochastic. So in the actual physical system, there are fluctuations present, and they can be important, and they are lost by reducing the attention just to the deterministic limit rho bar. And these 2 points I would like to take up again here on the next slide, so we can formulate them precisely. The first one would be the rate of convergence, which actually can be classified precisely in terms of a central limit theorem, which tells us that in some sense the distance or the approximation error we make when just taking this limit rho bar as the approximation to the actual system, it decays like the square root of the particle number. So this would lead to the first aim, namely to come up with an improved or corrected continuum model that allows to see a higher order of approximation in this error estimate. The second point addresses the point that in the hydrodynamic limit, so this deterministic limit, all of the information about the fluctuations around this limit are lost. And these fluctuations can be important. So at the one side, we know that they are rare because we know that the stochastic object, the particle system, concentrates on the deterministic object, but they are still present and they can have a significant impact. So for example, these fluctuations can be the cause for reaching tipping points of the dynamics and therefore switching in between different locally stable regimes of the dynamics, causing effects like metastability. So therefore, these rare events are rare but still relevant. And this leads to the second aim, namely to identify a correction to the continuum model which correctly displays the large deviation behavior in the sense that it has the same large deviations as the microscopic system has. Okay, so accepting these 2 aims, the question becomes what should be the correction to the continuum model? And the ansatz is a sort of infinite dimensional Langevin equation, which I write here. So we see that this is a superposition of the deterministic dynamics we had before. So on the left-hand side here, we just have the same nonlinear diffusion equation as on the last slide. And now it's corrected by adding this kind of stochastic perturbation. And the stochastic perturbation is of a particular kind. So we see that it has a derivative outside, so it's conservative. And it acts on a nonlinear function of the solution. So in classical deterministic PDE theory, you would call this a conservation law. And now the particularity here is that it also interacts with a stochastic term dW, which in this case is space-time white noise, amounting to saying that there is a zero correlation range in space and time. And this is why this kind of stochastic perturbation is typically called a stochastic conservation law, which we have added here. Now, the reason why this is expected to be the correct way to add fluctuations to the hydrodynamic limit can be understood from different directions. The first one would be coming from physical reasoning, namely in terms of a so-called fluctuation-dissipation relation, which prescribes how the dissipation term here with the nonlinearity in phi should correspond to the fluctuation term, and this precisely prescribes, for example, this structure of having the square root of the nonlinearity here as a multiplicative diffusion coefficient. So from physical principles, it's rather easy to come up with this form of a correction, and then we can maybe take an informal point of view, appealing more to mathematicians, that we can check consistency in the sense that at least informally, this stochastic correction, it should lead to the correct central limit fluctuations and informally again to the correct large deviation behavior in the sense that the formal CLT and large deviations that you derive from this SPDE coincide with the underlying particle process. Okay, so now the question is, well, what can we actually say rigorously? And there problems start because this ansatz, which I've written down, this would be called a singular stochastic partial differential equation because of the irregularity of space-time white noise. So this irregularity of space-time white noise, which comes in here and then even is hit with a derivative, so it even becomes more irregular, this causes this equation to become what is called supercritical. So it does not fit into this theory of regularity structures, which was introduced by Martin Heira precisely in order to prove well-posedness of solutions to singular SPDEs. So Martin Heira's theory applies to the case of subcritical SPDEs, but unfortunately here we are not in this regime. It's really supercritical, and therefore the very basis of regularity structures, namely the idea that locally at least solutions to singular SPDs can be well described in terms of expansions around a linear stochastic equation, this is not expected to be true here. Now, even if by some magic we would be able to generalize the theory of regularity structures to the case at hand, we would still face the obstacle of renormalization, because in singular SPDs you typically don't solve actually the original SPDE, but you have to subtract diverging constants in order to account for ultraviolet divergences. And these renormalization terms then in principle can also appear in the rate function, which would lead to wrong predictions. And this has been understood in maybe related models, more from quantum field theory, in work by Martin Heyer and Henrik Weber, where it is shown that actually these renormalizations indeed can happen to appear in the large events. Now, the good news is that in writing down this ansatz, we sort of overcomplicated the matter, because we made the ansatz with the space-time white noise, saying that the decorrelation length in space of this noisy perturbation is 0. And if you now take a step back and go back to the discrete system, then you see that while the effect of noise is independent on each of the grid points, it is constant on each of the cells. And the cells have a length of order 1 over n, so the decorrelation length of the noise actually should behave like 1 over n. Which would mean that instead of looking at the stochastic PDE I've written down up here, we would see a stochastic PDE where at the same time we have an amplitude of the noise, 1 over square root n, which goes to 0, and at the same time correlated noise, w, with a correlation length 1 over n, so also the correlation length at the same time goes to infinity. Also the cutoff goes to infinity and the correlation length goes to 0. So this justifies the next ansatz, which I've written down here. So we see that we replace the space-time white noise by a correlated noise where we have introduced a new coefficient k, which now quantifies the decorrelation length. And the decorrelation length here would correspond to 1 over k. And now we would be interested in the joint limit when the amplitude of the noise goes to 0 and the ultraviolet cutoff k goes to infinity. So this settles the question of modeling and what we expect to describe a good model to incorporate fluctuation corrections to the continuum model of a nonlinear diffusion equation. And now we can start developing rigorous mathematics for this. And the first question we have to answer is whether there actually is a unique solution to these kind of stochastic PDEs. So this goes back to a rather long line of work initiated by Lyons and Tsouganidis in the late 90s. Actually, in these first works, they were looking more at stochastic Hamilton-Jacobi equations, and then in the later works, together with Benoit Pertram, they took the viewpoint of looking at stochastic conservation laws. And starting from these initial works, then a line of developments emerged, reaching, in a sense, maturity in these last two works as part also of this group, in the sense that in these last two works, we can treat well-posedness to actually this full stochastic PDEs as it's written down here. So now we know that there is a unique solution to this stochastic PDE, and now we can ask whether we can actually make rigorous some of the informal justifications which I have laid out above in order to justify this ansatz as a fluctuation correction to the nonlinear diffusion equation. So in particular, we can ask the question whether rigorously one can actually show that the large deviations events are correctly captured by the continuum model. And this is the main result which I would like to present here. This is work jointly with Ben Fairman. And in this work, we prove a large deviation result for the solutions to the stochastic partial differential equation, which we have seen on the last slide, in the joint scaling limit when the noise amplitude n goes to 0 and the ultraviolet cutoff k simultaneously goes to infinity. And we prove that these large deviations are described in terms of a rate function, and this rate function coincides with the rate function that is known to dictate the rare events of the underlying particle process. So in this sense, the informal justification that the fluctuation correction that we propose is the correct one can be rigorously justified in this setting. And this can be seen as a particular case where the general link in between the theory of macroscopic fluctuations, one general theory to capture fluctuations or to describe fluctuations in non-equilibrium systems put forward by these authors in this nice overview paper, can be rigorously linked to the concept of fluctuating hydrodynamics as it has been used, for example, by Landau and Lifshitz, really in fluid dynamical situations, and by Herbert Spohn in many publications, where the viewpoint of fluctuating hydrodynamics describes fluctuations in non-equilibrium systems in terms of formal stochastic partial differential equations. And the formal link in between these two theories is precisely that if you believe that fluctuating hydrodynamics makes the correct prediction of the fluctuations, and then you formally write down a large deviation theory for these singular stochastic PDEs, then you would recover the rate functions, which are the starting point of the macroscopic fluctuation theory. And in the particular result that I've presented here, we make this link precise by proving a large deviations result for the underlying stochastic partial differential equation. So this lays out how non-equilibrium statistical mechanics is linked to singular limits of stochastic partial differential equations. And now, having a short look at the proof of this result, we further see the link to theory of nonlinear PDEs with irregular coefficients. Namely, when proving this event or this result on large deviations, the crucial ingredient is actually to understand the so-called skeleton equation in terms of well-posedness and stability. And you see the skeleton equation, it looks very similar to the stochastic PDE that we have been considering, just that now the space-time white noise that we have in the singular SPDE is replaced by this control G, where G is just an L2 function. So this makes this stochastic PDE, so this makes this PDE PDE with irregular coefficients because G is not a continuous function but just an L2 function. And this is not an arbitrary choice, but the choice of controls G being in L2 here just amounts to the fact that the Cameron-Martin space of space-time white noise is exactly the L2 space. So the challenge is to prove the existence and uniqueness of solutions to this skeleton equation. And in order to get an idea whether this is a complicated or difficult task or not, a good thing to do is to argue or to have a look at scaling arguments, meaning that we zoom into this equation and have a look at which term, so whether the diffusive term, which would improve regularity, or the hyperbolic or convective term with irregular coefficients, which would lower regularity of the solutions, dominate on local scales. And what we see is that the criticality behavior of this PDE, it depends on the integrability and regularity that we prescribe for the control G. And in fact, here we have good and bad news, namely, based on the scaling argument, one can see that G being in L2 is precisely the energy critical state, meaning that also on local scales, neither of these operators wins, but both of them are equally present also on local scales. So this is bad news in the sense that we cannot say that this is actually a perturbation to a diffusion equation, which would mean that we can treat it with classical techniques. But it's also good news because it's not supercritical, so there is hope that actually well-posedness can be shown. So one particular challenge here in this well-posedness treatment is the proof that concentration of mass is avoided in terms of establishing regularity estimates. And in a nutshell, we prove then well-posedness of this equation by developing what you could call a nonlinear generalization of the theory of renormalized solutions introduced by DiPerna-Lions, for example, in the context of linear transport equations. Now we apply this to nonlinear equations, which means that new commutator estimates appear by commuting convolutions with nonlinearities. And these new commutator estimates have to be treated and understood. And this is based on new optimal regularity results that we develop for these equations. And in fact, then to prove the uniqueness of renormalized solutions, or so-called kinetic solutions, also hinges upon a new proof, since the classical methods don't apply here. So there's an additional part which, if you want, extends the theory of kinetic solutions introduced by Lyons, Pertam, and Tadmor to this case of PDEs with irregular coefficients. Okay, and this finishes this short overview of this result, and I hope that it has become clear how in this question the different fields of statistical mechanics, stochastic PDEs, and nonlinear PDE theory come together. Thank you.